Okay, so we gave the basic idea behind public key cryptography and some hard problems. Let's say a hard problem called Knapsack problem and see how can I design an encryption algorithm using this idea. By the way, this is not a good idea. I mean, it is broken many times in the past. Many times people modified this idea. But since it was broken badly many times, so generally we don't trust it and we don't use it. So if you come up with a better way to, modify this algorithm, yeah, it can work, but most of the people not use it. So knapsack problem is as follows. You have a set A, which contains numbers AIs. These are integers, positive integers actually. All of them are, as you can see, are greater than equal to 1. And you are given an integer s. Generally, this is a large integer. So question is, can I sum of these AIs and obtain the value s? So as you can see, this is a summation epsilon I times AI. Epsilon is just 0 or 1. So you just determine which AIs you want to add to it and obtain the s. So does there exist such a set of epsilons so that this summation gives you s? This is the question. So we call it knapsack problem. So think about s as the size of your knapsack, a bag. And you have very many items of sizes AIs. Questions, can you fully fill the bag with some of these items you have? Okay. Search version with the same input, either find epsilon AI such that this gives you the summation. Okay. So decision problem asks you if there's such a solution. Search problem asks you to give us these AIs or epsilons, depends on which one. So knapsack decision problem is NP complete. This means that this is really hard. Map any NP hard problem to this one and so on. So if you can solve this one, you can actually solve all of these NP problems. So this also solves the huge open problem, like is P and NP are different sets or identical. So this is it also tells us, can we solve every problem in a fast way? If you can solve NP complete problems in polynomial time, this means that you can also solve almost anything in polynomial time, right? Okay, so let me show you a cryptosystem, knapsack public key cryptosystem, which is based on this problem. Okay, it was proposed by Merkel and Hellman in 1978 and cryptanalyzed by Adi Shamir in 1982. Key generation works like this. Choose a super increasing sequence AIs. So here I use the new term, super increasing. This means that sum of the first k-1 AIs should be less than the next AK, okay? So, A2 should be larger than A1. A3 should be larger than sum of A1 and A2, and so on and so forth. This is what we mean by super increasing. You choose a modulus M, which has to be larger than the sum of all of the AIs here. You choose a multiplier W, which has to be between 1 and m-1, and the greatest common divisor of W and M should be 1, so they have to be co-prime or relatively prime. So you do the computation as follows. You multiply all of these AIs with W and calculate mod M and obtain BIs. So I think as you can see what is going on, you are going to actually hiding the values of AIs by choosing these two values and making this computation and obtaining BIs, okay? Your public key will be BIs, but only you know AIs, and also the values W and M. And this would be enough for you to encrypt and decrypt, okay? So since public key is BIs, people are going to use it to encrypt a message, and you will use this to decrypt it. So let's see an example. So in encryption, a message is going to be represented as bits, MIs. And ciphertext is calculated as follows. BI times MIs, and all of them are summed together. Recall that BI was the public key, MI is your message, so the person who is going to encrypt it doesn't need anything else, okay? So the decrypting person will multiply C, the ciphertext that is received, with W inverse modulo M. Okay. And obtain S. And then solve the super increasing knapsack with having the AIs and S. Okay. Why decryption works? This is just, actually number theory. The decryption is actually, the C is actually MIs times BIs, right? But BIs are actually W times AI. So if you multiply C with W inverse, you mean that you are putting W inverse here, they cancel each other, so you end up with MIs times AIs. Okay. So let me show you an example. Assume that I chose the private key as like this. So this is super increasing. As you can see, 7 is larger than 2 plus 3. 15 is larger than 2 plus 3 plus 7, and so on. So I chose M equals to 61, W equals to 17. And by calculating BIs, it turns out that this is the BIs, okay? So this is your public key now. So you announce it, and the person who wants to send me a message is going to send me this one, let's assume, okay? So C is actually 0 times 34 plus 1 times 51 plus 1 times 58 plus 0 times 11 plus 1 times 39. So they calculate the ciphertext and they send it to me, okay? What I do next is follows. Recall that I have to multiply it with W inverse. In our case, it is 18. You can check if you want. Modulo M, which is 61. Turns out this is equals to 41, modulo 61, okay? Now what you're going to do is to solve this using the super increasing sequence AIs. So now we are going to do the knapsack problem and see which some of these AIs actually tell me 41. So since this is super increasing, first you do the following. You check if 41 is larger than the largest value in this private key setting. So yes, 41 is larger than 31. So you say that, okay, my bit has to be 1. Then I subtract 31 from 41. It is 10. Next step is checking if 10 is larger than the previous value, which is not. So I tell that this bit has to be 0. Then I do the following. I check if 10 is larger than 7. Yes, then bit has to be 1. Subtract 7 from 10. It is 3. Check if it is 3 larger than or equal to 3. Yes, then I say 1. I subtract is 0. So 0 is not larger than 2. I say that the last bit is 0. So think about epsilon i's I obtained. 0, 1, 1, 0, 1. This is the message that are sent. So as you can see here, I solved the knapsack problem. So the thing about our initial starting point, I wanted to rely my security on a hard problem, and I chose knapsack problem, right? Now I'm using it to decrypt the message. So if it is MP complete, how this crypto system can be broken? Does this mean that you actually also solve the knapsack problem? The thing is that in the knapsack problem, recall our problem. Let's go back. We start with an input A, where it contains an integers AIs. Here we are not saying anything about super increasing, right? So every instance of this problem is not that easy. But once you modify the problem and say that we are going to focus on values which are super increasing, now you modified the problem. So at this point, it is not MP complete. And this is why it is easier to break this system, and actually Shamir broke it in a very nice way. So this is why you shouldn't be using it in practice. But a nice example to see how you can design a public key, private key setting and obtain encryption and decryption.